Okay, equidistance theorems, 4.4 in your books if you want to follow along. Okay, the objective of this lesson is to recognize the relationship between equidistance and perpendicular bisection. Basically, what this is going to do is save you a multitude of steps, and I'll give you an example of that towards the end, and then I'm going to leave you with a proof that we've done previously that took, I believe it was 11 or 12 steps that you're going to be able to knock down significantly using this, and I'm going to want you to do that on your own. So anyway, moving right along. Okay, distance. Definition: distance between two objects is the shortest path joining them. Okay, and the postulate that goes along with it is a line segment is the shortest path between 2 points. We know this, okay? Pretty fairly straightforward, but where that comes into play is equidistant. Now, I know we've touched on that briefly. A bunch of people asked what equidistant meant. Okay, if 2 points P and Q are the same distance from a third point X, the X is said to be equidistant from P and Q. So you could say that PX and PQ are congruent, and it means that X is equidistant from P and Q. Sorry, it should be an and, not an and. And we could show that with our symbols here. Easy enough. Okay, and the second part of this is the perpendicular bisector, which again, you guys have worked with before. You've had to prove it. Okay, definition: perpendicular bisector of a segment is the line that bisects and is perpendicular to that segment. Okay, the theorem that goes along with it, though. Now, these are the equidistance theorems. So theorem 24 states that if 2 points are each equidistant from the endpoints of a segment, then the 2 points determine that the perpendicular bisector of that segment, sorry, that was a little wordy, basically means if you've got 2 points and they are both equidistant from another 2 points, then they determine the perpendicular bisector, and what that's going to do is save you a multitude of steps. Okay, the second part of that is if a point is on a perpendicular bisector of a segment, then it is equidistant from the endpoints of that segment. So it's kind of like, it's similar but not the same, showing you different parts of it. And that's theorem 25. Now, how does this all apply to you? What does it even mean? I've probably lost at least half of you by now, but to see it actually used in a proof might help. So we've had this one before. We're given that ABC, triangle ABC is isosceles, with segment AB being congruent to segment AC, and that E is the midpoint of segment BC. And we need to prove that line AE is perpendicular to segment BC. All right, now what we would do is, of course, start with our givens, and then we could say that BE is congruent to CE by the definition of the midpoint, which states that the midpoint of a segment divides the segment into 2 congruent segments. And then we would go on to say angle B is congruent to angle C, because if 2 sides are congruent, then their opposing angles are congruent, or just my little diagram that I love to draw for whatever reason. Then we would have triangle ABE is congruent to triangle ACE by side angle side in steps 1, 3, and 2. And we could show that angle BEA is congruent to angle CEA by CPCTC. Okay, this is what we've done before. This is exactly how we've done it in the past. Then we would say that angle BEA and angle CEA are right angles, because if 2 angles are both congruent and supplementary, then they are right angles. And we'd finish it off with line AE is congruent to segment BC, because if 2 segments form right angles, they are perpendicular. Okay, that's what we've done before. Watch this. This is awesome. It's going to blow your mind. Same proof. Same thing we have to prove. Start off with the same given. Triangle ABC is isosceles, with AB being congruent to AC, and E is the midpoint of segment BC. Then we would say that segment BE and segment CE are congruent because the midpoint of a segment divides the segment into 2 congruent segments. Easy enough. But now here's what we're going to do. Because I now know these new theorems, let's see, I've proved 2 endpoints right there, and I've proved another 2 right there. So I said that these, I shouldn't say two endpoints. I've proved that this is equidistant to that, and we're given that B is equidistant to A as C is equidistant to A. So those two are all equidistant. Okay, so we have 2 points that are equidistant from the same A and the same E. So we can say that, oh look, line AE is perpendicular to segment BC because 2 points each equidistant from the endpoints of a segment determine the perpendicular bisector of the segment. Real wordy, I know. But basically what you need to know is, oops, okay, I've got these 2 points here. Okay, if I can prove that they're equidistant from this point and that they're equidistant from this point, okay, then I can say that this segment and this segment form a perpendicular line or perpendicular bisector because of theorem 24, I believe, yes, theorem 24, okay? So that's how you use it to shorten it up. I mean, we can go back to our previous slide and we had 7 steps, and then all of a sudden we've got 3. And notice I put this here because I've got to prove equidistance from 2 separate points that are on the same segment or line. So make sure you do that, and doing that little, point there, drawing that in, sometimes helps. So what I'm going to leave you with now is this. We've done this one before, and I guess it would help if I labeled this. Let's call that O. This would be B then. This would be C. And this would be A. And we're going to make that, I believe it's supposed to be E. Sorry, I don't have my tablet with me right now, so this is what I'm relegated to. But I want you to go ahead and, like I said, this was like an 11 or 12 step proof, and I want you guys to knock it down using what you've learned. So go ahead and try and do that. I want you to bring it in. I'll be collecting it right at the beginning of class on Tuesday. Okay, so have a good one and enjoy your day off tomorrow.